Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting topic in 8086 microprocessor. We're going to see architecture of 8086. So before going to this video, we already posted the video regarding features of microprocessor and register organization of 8086. I would recommend you people to go through that video first and come back to this video so that you can understand how the register is organized, how the memory is organized in 8086, so that you can understand the architecture very clearly, right? So this is the architecture of 8086, where in 8086 we have two important units. One is bus interface unit and execution unit. Bus interface unit, from the name itself you can understand, bus interface unit establish the communication between peripherals and the memory. It initiates the read and write cycle operations, and very importantly, bus interface unit fetches the instruction from the memory and stores the instruction for execution, right? Whereas the execution unit, it will execute the instruction which is fetched by the bus interface unit, right? So you'll see the important elements of bus interface unit, where bus interface unit, it has instruction byte queue and it has segment registers, and it has provision to identify the physical address, right? It can able to interact with the memory interface. And when it comes to execution unit, it has control system where it provides the control signal for all the operations, and it has arithmetic logic unit where the arithmetic and logical operations will be taking place, and depending upon the address of all the ALU operation, the status of ALU will be seen in the flag registers, right? It has flag register as well. And apart from it, the execution will have the register unit where you have general purpose registers and you have pointer and index registers, right? I have already explained about the register banks of 8086, what is general purpose register and what is pointer register, what is index register, all those things. Please go through it. Right now we will see bus interface unit first. These are the two units which we just explained, which is bus interface unit and the execution unit, right? As I said, bus interface unit, where it fetches the instruction, read, write from the memory and IO ports, right? So all these operations is carried out by the bus interface unit, right? And very importantly, it has the instruction queue, where the instructions, it has up to 6 byte of instruction queue. That is, it has 6 byte instruction queue where it can able to fetch 6 byte instructions, and it can store that instructions in this particular instruction queue, right? So that the instruction at a time, we can able to have 6 instructions in this particular instruction queue, and the execution unit will execute the instruction from this instruction queue one by one, right, in first in first out method. Okay, and because of this instruction queue, by design 8086 supports pipelining. That is, it already prefetches the instruction, and so that the execution unit can be process this instruction parallelly. That is, the execution unit can parallelly process this instruction, like one instruction will be fetched and the other instruction will be executed. So it supports pipelining so that the instruction will be executed a little faster, right? So by design 8086 supports pipelining. And apart from it, it has segment registers. I already explained the memory of 8086 is split into 4 different segments, which is code segment, data segment, stack segment, and extra segment, right? And these segments can be accessed using this segment registers, right? And very importantly, in this particular bus interface unit, we have IP, which is instruction pointer, where instruction pointer tells you what is the next instruction that is going to be executed, right? And these segment registers are very useful to identify the physical address. As I said, this address generation, it helps to identify the physical address. Physical address is 20-bit physical address. in 8086. It identifies 20-bit physical address. I've already explained how to determine the physical address, but I'll also explain here again. Right, it's 20-bit physical address. That is, the physical address can be calculated using this formula. Physical address is equal to segment register into 10H plus offset pointer. Right, so in order to determine the physical address, right, to identify the physical address, these segment registers are used, right, and these segment registers, each of the segment register are 16 bits, whereas the physical address is of 20 bit, and the remaining 4 bits will be given by the offset pointer. Right, I'll come back to this offset pointer when I explain the registers here. Right, so in bus interface unit, you got to explain about this instruction queue, and then you got to explain about the segment register, right, and you got to explain about the address generation. And when it comes to execution unit, right, the very important thing is it has the control system where it provides the control signal for all the operation, right, and this instruction will be decoded by using this control system, and while decoding, it will supply the control signal for executing that particular instruction. And very importantly, we have ALU which performs arithmetic logic unit, right, which performs arithmetic logic operation, and based upon the result of ALU, right, the flag register will be enabled, the corresponding flags will be enabled, right. We have 16-bit flag register in 8086. Right, I'll explain the complete flag register in detail. And apart from this execution unit, this ALU and internal control system, very importantly, it has general purpose registers. When it comes to general purpose registers, we have 4 important general purpose registers, which is AX, it can be represented as AX, BX, CX, and DX. Right, so all these are 16-bit registers. Right, and when we say it as 16-bit, we can call it as AX, BX, CX, and DX. But it will be separated into a lower byte and higher byte. AL and AH, BL and BH, CL and CH, DL and DH. Right, where AL is nothing but it will act as an accumulator. This AL will act as a default 8-bit accumulator, where AH will act as a default. Where AX will act as a default 16-bit accumulator. AX will be acting as a 16-bit accumulator default, and AL will be acting as a 8-bit accumulator, default accumulator. And BX, it is used to store the base address, right? These base address, and whenever we use indirect addressing, like we can use this particular register to save the base address. And similarly, this register, CX register, it is used to store the count values. Whenever we use branching instruction, looping instruction, the count values will be saved in this particular register. And DX is used as a default destination, right? Whenever we use implicit operation, implicit instruction, and also if you perform a 16-bit multiplication, that is, if you perform 2 16-bit multiplication, you will get a 32-bit result, where the 16-bit will be saved in accumulator and remaining 16-bit will be saved in the default destination, the D register, right? So we will see all this register in detail one by one, right? And apart from this general purpose registers, we have pointer and index register, where the pointer register, source pointer and base pointer, right? And index pointer, we have the destination index and as well as source index, right, where this pointer register can be used to access the stack segment, where SP is used to access the top of the segment. It gives the address of the top of the segment, and the remaining address can be accessed using BP. And similarly, DI and XI, right, where SI can be used for data segment and DI can be used for extra segment, right? That is, I already explained about this offset pointer, where whenever we need to calculate, whenever the 8086 calculate the physical address using segment register, if it uses CS, then IP will act as an offset pointer, IP will act as an offset pointer, and whenever it uses DS, then it will use SI as offset pointer, and similarly whenever it uses ES, it will use as a DI as the offset pointer, and similarly whenever it uses SS, SP and BP will be acting as an offset pointer. This is the overview of both the bus interface unit and as well as the execution unit, right? And as I said, we have a dedicated address generator, that is, it can able to identify 20-bit address that is identified by using these segments: code segment, data segment, stack segment, and extra segment, right? And when it comes to segment registers, I already explained what is segment register. That is the memory of 8086 is split into 4 different segments. To save the code, we have code segment, and to save the data, we have the data segment, and for stack memory, we have stack segment, and for storing the extra data, we have extra segment, right? And this segment can be of a continuous like this, right, or it can be partially overlapped. Like you can see the partially it is overlapped up to here, it is overlapped with the other segment, or it will be fully overlapped like this, or it will be disjoint, right? And this memory, that is the 8086 is of 1 MB, right, and it has been divided into different segments, each of which have 64 kilobytes, and 8086 can directly access the 4 segments, as I said, these 4 segments through this particular registers, right? Program obtain access to code and as well as data by changing the segment register content, right, to a point to the desired segments, right? The corresponding segments can be accessed through this segment register, right? The corresponding memory segments can be accessed through this segment register, right? And now we will see each segment register separately. Whatever I explained before, that is given as points here. That is, you can see here code segment register, it is a 16-bit, right, and it contains the base and start of the code segment, and the IP will be acting as the offset pointer for this particular code segment. And BAE computes 20-bit physical address, right, by logically shifting the content of CS4 to the left, and then by adding 16-bit contents of IP. That is, I have already given you a formula, that is physical address is equal to, right, segment register into 10H plus the offset pointer, right, offset pointer. And you can also say in this way that instead of into 10H, right, we can able to shift the content of that particular segment register, so that we can able to obtain this particular operation, very similar to this operation. That is what given here, right? So that is about code segment register. And when it comes to data segment, again it is a 16-bit register where it points out the current data segment, right? And it uses, as I said, it uses the source index or the destination index, but more probably it uses source index as the offset pointer to calculate the physical address, right? And when it comes to stack segment register, it points out the current stack, and 20-bit physical address can be calculated using these 2 pointers, that is stack pointer and as well as the base pointer, right? Whereas stack pointer represents the top of the address, that is top of the stack address, whereas the other address will be represented by this base pointer, right? And next thing is extra segment register, where extra segment register, it is also a 16-bit register where it points out the extra segment in each data, right? And here the offset for extra segment will be DI, destination index. I already explained that whenever we use a segment, extra segment register to identify the physical address, then DI will be used as a offset pointer, right? And similarly the instruction pointer, it always is 16-bit, and it represents the current next instruction that is going to be executed, and this will be acting as an offset for code segment. It will be acting as an offset for a code segment, right? And apart from this, I have explained about the instruction queue. As I said, the instruction queue will be the instruction will be fetched and it will be saved in the instruction queue, and it will be executed in such a way that first in first out method. right? And this this instruction queue will help in speeding up the operation. That's because of this instruction queue, the 8086 supports pipelining. That is, the bus interface unit and as well as the execution unit can work parallelly so that the instruction will be executed at a greater speed, right? And when it comes to execution unit, I've explained what are the components of execution unit. We have ALU, we have this general purpose registers. When it comes to general purpose registers, we have 4 general purpose register, and we have pointer register, stack pointer, and as well as base pointer, and as well as the index register, which is source index and destination index, right? And when it comes to general purpose registers, we can call it all this as AX, BX, CX, DX or 16 bits, and we can also split that into AH, AL, BH, BL, CH, CL and DL. And I already explained for each registers that is what is the operation of each and every register, right? When it comes to accumulator register, as I said, it is 2 8-bit register where AL can act as a default 8-bit accumulator and AX can act as a default 16-bit accumulator, right? And we can also use 8-bit data and as well as 16-bit data. And similarly, base register, whenever we use indirect addressing, we can go for this particular base register. That is, once again, it has two 8-bit register BL and BH, and combined it can be called as BX, where it is a 16-bit, right? And BL represents the lower bit and BH represents the higher bit, right? And whenever we go for indirect addressing, this register can be used, right? And similarly, CX, as I said, it can be used for a count values. That is, CL and CH, it is a 2 8-bit register combined to form a 16-bit register, and CL is a lower byte and CH is the higher byte. And these instructions, shift, rotate, loop instruction, CX can act as a counter, as I said, right? So, and the last one is a DX, it is data register. We can call it as default destination, and as usual it is DL is 8-bit and DH is 8-bit, right? And whenever you perform a 16-bit multiplication or division, the extra bits can be by default saved in this particular register, right? And when it comes to stack pointer and base pointer, it is used to access the stack, where the SP is used to give the highest stack address, whereas BP can be used to access the other address in the stack, right? And I have already explained whenever the SP and BP can be used as an offset pointer for the segment register, right? Whenever we use the segment register to calculate the physical address, right, then these can be act as a offset pointers. And similarly, source index and destination index can be acting as a offset pointer for data segment and as well as the extra segment, right? And this is source index and as well as destination index, where this points to the data segment and this can point to the extra segment, right? And similarly, the source index and destination index can be used in index addressing as well, right? And we have already seen general purpose registers. We have seen the stack pointer registers, that is stack registers, general purpose registers, and we have seen what is a pointer and index registers. Now we will see about flag register. When it comes to flag register, it is a 16-bit flag register. It has conditional flag. It has 9 flags totally, where we have 3 control flags and 6 conditional flags. What is conditional flags? Depending upon the result of the arithmetic or logical operation, these condition flags will be enabled. And the control flags have a separate control operations, right? You can see here CF is nothing but carry flag, and PF is parity flag, AF is auxiliary carry flag, ZF is zero flag, and SF is sign flag, OF is overflow flag. And these are the 3 control flags, where trap flag, interrupt flag and direction flag, right? Where CF, this carry flag, we already know that carry flag will be enabled whenever there is a carry in the result. That is, after performing the arithmetic operation, if there is carry in that particular result, then this particular flag will be enabled. right? And this parity flag, whenever there is an even parity of ones in the result, then this flag will be enabled, right, to indicate it is an of even parity. And if it is odd parity, it is set to 0. And similarly, whenever there is carry between lower nibble and higher nibble, right, then this auxiliary carry flag will be enabled whenever there is a carry from lower nibble to higher nibble. And 0 flag is enabled whenever the result is 0. And sign flag, whenever there is a negative sign that is indicated by this particular sign flag, it indicates the negative operation, right? And TF flag, it is the control flag, which is the trap flag. This trap flag is enabled whenever the processor enter into the debugging mode. It helps the microprocessor to enter into the single step operation mode, that is debugging mode, right? And interrupt flag, I already explained that this interrupt flag, whenever there is an interrupt, this flag will be enabled, and only the interrupt will be served if the interrupt flag is enabled, the IF is equal to 1, right? And the next one is direction flag, and it is used for string operation. Whenever there is an string operation, we use this particular flag. It represents the direction, that is from higher memory to lower memory, or from lower memory to higher memory, right? Whenever there is string operation from higher memory to lower memory, then DF will be is equal to 1, and if it is from lower memory to higher memory, then DF is equal to 0. This is about the flag register. So whatever I said, right, that is explained here. So you can see the carry flag, where the carry flag is set when there is a carry in the particular result, right? That is MSB is 1, right? And if it is borrow also, this flag will be enabled. And if there is even parity of number of ones in the result, then this flag will be enabled, parity flag. And what is auxiliary carry flag? Whenever there is a carry from lower nibble to higher nibble, then this flag will be enabled. What is 0 flag, right? If the result of the computation is 0, then this flag will be enabled. And what is sign flag? Whenever there is a negative, right, there is a negative sign in the result, then that will be indicated by this particular flag. And TF flag, as I said, it helps the microprocessor to enter into the single step execution mode, which is a debugging mode, right? And interrupt flag is enabled whenever there is an interrupt. And similarly, the direction flag, if this flag is set, it is used for string operation mostly. If this flag is 0, then as I said, the string operation is processed from lower address to highest address, and if it is 1, it will be processed from higher address to lower address. And the last flag is overflow flag. Whenever there is overflow of data after the arithmetic operation, then this particular flag will be enabled, right? So this is about the flag registers. So overall, this registers can be categorized into 4 different groups, where you can see general purpose registers, pointer register, index register, and you have separately called as instruction pointer, and we have segment registers, and we have flag register. And all this are 16-bit registers, but the general purpose register can also be accessed as an 8-bit register separately, right? And this is the function, the complete function about different registers, where you can see AX can act as an 16-bit accumulator, AL can act as a 8-bit accumulator, BX base register, CX can act as a counter register, and DX can act as a data register. SP is nothing but stack pointer, which holds the address of the top of the stack, whereas base pointer holds the address of the other address of the stack, right? And source index, as I said, it is used in string operation to hold the source operand, and similarly it holds the destination operand. And apart from it, this can be used as an offset pointers for the stack segment, right? This is the summary about the different registers, right? So what we have seen today is, we have seen the architecture of 8086, right? So this is very important question in this particular unit. Definitely you can expect 8086 architecture, right? Hope this video is useful for you. Thank you, my dear students.